Hey guys, welcome to Objective 1.1, Implementing Multithreading and Asynchronous Processing. Today's objectives are understanding threads, using the task parallel library, using the parallel class, using the new async and await keywords, using parallel language integrated query, or plink, and using concurrent collections. So before we could fully understand threads, we need to take a look at the bigger picture of the whole operating system and how the operating system functions first before we can fully understand it. So let's take a hypothetical situation. Let's say we had a computer and our computer has one CPU and our CPU only has one core, so it's a single core processor. If we created an application on this single core processor that performed a long operation, so let's say it was going out and doing some mathematical equation that took maybe a minute to complete. If we weren't using the Windows environment and using the capabilities of Windows, that operation that it would take, well, that operation would cause the whole computer to freeze up and seem unresponsive because the CPU is giving that application its full amount of time on the CPU. So when that operation is running, the Windows would seem frozen, everything would seem unresponsive. Now, because of that problem, Windows obviously has a solution for that. And Windows' solution is they created a service called the Windows Scheduler. And the Windows Scheduler's job is to simply make sure that to make sure all applications and all threads have a fair amount of time to run on the CPU. Now, because of the Windows Scheduler, if we took that scenario again where we had an application with a single core processor that did a long operation, if we did that same thing but we used the Windows Scheduler service, everything would still seem responsive, right? So our application would go off, it would be doing its long operation, and the Windows Scheduler's job would be to, okay, say our application can run for a set amount of time. After that set amount of time, then another application runs. After that, another application runs. After that, the operating system has some time, whatever. So the Windows Scheduler goes around giving everything a fair amount of time. Now, if you do that at a really fast, rapid speed, like extremely fast speed, it creates the illusion that everything is running at the same exact time and that everything is fully responsive. Because if you give every single thing a set amount of time and then keep on rotating in a circle, giving everyone time on the CPU, on the single core processor, it creates that illusion that, everything, well, one, it looks like everything is running at the same time. It looks like my application that I created and another application that I'm using are both fully functional. And I mean, in turn, they really are fully functional, and that's what the Windows Scheduler's job is. The Windows Scheduler's job is just to make sure everything has a fair amount of time. Without the Windows Scheduler, if one application was running, everything else would pretty much be frozen. Now that we know that, we can dive a little bit deeper into the programming and how we as programmers have to use this concept of threads to make our programs more realistic and more reliable. So the first thing to note is when we create applications, let's say we're creating an application that has a graphical user interface, right? So in those types of applications, there's always a main thread, right? We have our one main thread. And our main thread's job is to do whatever code we type in on the main thread and also manage anything else. So like if we're building a graphical interface, the main thread's job would be to make sure that the graphical interface is always responsive, and the main thread will be running the graphical interface. So when we're creating a graphical interface application, if we code something that does a long operation on the main thread, it would cause the graphical interface to be frozen and unresponsive because it's all in the same thread. When the Windows scheduler comes in, it gives that one thread time on the CPU, but because that one thread is doing a long operation, the main thread, which is also responsible for the graphics, gets frozen as well. So that's the problem with just running everything on one thread, right? The Windows scheduler is in place to, create a good environment that everything is responsive. But if we don't use the advantages of the Windows scheduler, then our program can still suffer because the main thread is responsible for the graphics. So if we do long programming on the main thread, that will make the application seem unresponsive. So how we can fix that is by, if we know we're going to be doing a long operation, or if we know we need to do something, we can throw it onto a new thread. And by throwing it onto the new thread, when the Windows scheduler comes into our application, it will give the main thread some time, which is the graphical interface. It will give the main graphical user interface thread some time to run, and then it will then switch over and give some time to run on our long operation. So the Windows scheduler in that case will make sure that the graphical interface is responsive and our long operation is continuing, because like I said, the Windows scheduler has that ability to create that illusion that everything is running at the same time and everything is always responsive. Just because the fact that the Windows scheduler and the CPU goes so fast that just by giving everything a little amount of time and doing that over and over again, everything looks like it's fully running all the time. So when we have long operations, when we put it on a separate thread, then our applications will remain responsive. And that's like the really most important thing with multi-threaded programming as a concept, right? The whole concept is to make sure we could build applications that are always responsive to the user. We don't ever want the user to be sitting there and seeing a frozen screen. We always want it to be responsive. So that's why we use multi-threading. So now that we know what threads are and why we use threads, now we need to start learning how we can create threads as programmers, and we need to make sure that we are creating them in the right times. So the first way that I'm gonna show you how to create threads is by using the thread class. Now there are other ways that we're gonna get to, but the first way is using the thread class, and this is like directly interacting with threads. Like, we have the full power to create a brand new thread by using the thread class. So the first thing I'm going to do is I'm going to create a function. This function's job is going to be, when I create my thread, I'm going to attach a function to that thread so that when that thread runs, the thread will be running whatever code is inside my function. So I'm going to start by creating my function. So I'm going to go public static. I'm going to make a void function, and it's going to have no parameters. I'm going to call it thread method. No parameters. Inside of my method, I'm going to have a loop. It's a basic loop for int I equals 0 for as long as I is less than 10. I++, basic loop. And every time the loop iterates, I'm just going to go console.writeLine thread process, and we'll do a little placeholder. And I'm gonna put in the I, so whatever whatever up to in the iteration, and then I'm gonna do this thread dot sleep. Now this thread dot sleep is nothing to be scared of. It's pretty much just saying that. Remember how I said this? The Windows scheduler make sure that everything gets enough time on the CPU, right? The Windows scheduler has its own time set up in the code for the Windows scheduler, so it knows how to give every thread enough time on the CPU. But let's say we don't need all that time, right? So when this thread that we're creating right now gets time to run the CPU, once we run our console.writeLine statement, we don't need any more time, so we can recycle our time. So we can say thread.sleep 0, and that's just pretty much saying, okay, we're done for right now. Let another thread run on the CPU. So that's what we're saying. Of course, our the CPU is going to give us time again eventually, so we're going to get it back. But every single time we write the output, we're just going to say, okay, we're done. Give someone else some time on the CPU. So this is our method that's going to run when we create the new thread. So inside of the main method, I'm going to create the new thread. So the syntax for that is saying thread, then the thread name of it, so T, I'll call it, equals new thread. Now for the constructor, I'm going to pass in a delegate, and I'm going to pass in it's called a thread start, right? So I'm going to say new thread start, which is a delegate, and the delegate requires a function that has a return type of void and takes in no parameters, which that's what our function does. So I'll go ahead and pass in thread method like that. After we have our thread instantiated, let's go ahead and start the thread by going t.start, and that will start our thread. Now to prove to you that our thread is running, I'm going to do another loop on the main thread, right? The main thread is the program that is the main thread that we start out with. If we don't specify a thread to write our code on, we'll be writing our code on the main thread. So let's go ahead and make a loop again for the main thread this time. And on the main thread, I'm just going to go console.writeLine main thread do some work. So that's what we're going to display every iteration. And once again, I'll do that thread.sleep 0 to say that we're done. Let another thread run. So the last thing we need in this is we're going to add a t.join function call. We're going to go t.join. And pretty much what that's saying is, since we created another thread, when that thread goes off, the program flow of the main method will continue. So once we start it, it's not going to wait here until the thread's done. It's going to continue and then start whatever other code it has to do. If I didn't put this t.join, after it ran this for loop and it continued down, right when it exits the main method, the program would close. And then it will close all threads. Everything would be shut down. So by doing t.join, I'm pretty much specifying that don't go past this line of code until the thread that we created is done executing its code. So once we get past this t.join, then we know for a fact that this thread has finished its code. So by doing that, it's just waiting for our thread that we created to finish. So if we go ahead and run this code, we can see some output. We can see that it's running the code from the thread and then running it from the main thread. Maybe if we run it again, that time the main thread ran the first time. Let's run it again. Here this time we see some interlocking, so we see the main thread running, then the thread we created, and back and forth. So by this pattern, we can see that the Windows scheduler is on its own time, right? Whenever it gets its time to call it, then it does it. It's not always the same thing. Whatever the Windows scheduler is doing, then it will run. With the t.join, however, to show you what that is doing, if I go ahead and go after the t.join, if I go console.writeLine and I write like after, for instance, and I run this, no matter how many times I run it, after will always be the last thing to display because it's waiting for all the threads to finish by doing t.join. So I can run this a million times and after will always be displayed last. If I were to go ahead and delete or comment out that t.join and then run it again, we can see that after, look, it's not last anymore. It's not last because what happened was it went into the main method, it ran my for loop in the main thread, then it kept on going, nothing told it to stop, and it said after, right? And meanwhile it's doing that, then the other thread's running in the background, still going and doing its own things as well. So we can see that if we don't put t.join, it's not going to wait till this thread has finished before it continues. If I put it back in, we'll be able to see that when I run it, after is always going to be last. So that's what t.join does. It just waits for the thread that we created to finish before it continues on. Okay. So the next thing to note about threads, creating threads using the thread class, is that there are two types of threads that we can create. We can create a foreground thread or a background thread. Now, if we don't specify whether it's background or not, it's by default a foreground thread. So the threads we were using in the last listing was foreground threads. So now I modified the program slightly. I changed the thread function from sleeping 0 to sleep 1000, which is sleeping for 1 second. So every time it writes one iteration of the for loop, it will wait a second before it writes the next one. That's all that means. I also took out most of the code in the main function, and I just instead marked my thread as t.isBackground equals true. So by making a thread isBackground equals true, changes the thread from being a foreground to a background running application. A running thread. So now the differences between foreground or background are pretty simple. A foreground thread, if you go out and create a foreground thread off in the side, and the program is about to end, right? The program won't terminate until that thread is finished doing its job. Now, if you have a background thread, if you make a thread and throw it onto the background, if your program is doing whatever it's doing and then the program happens to close, then because it's a background thread, it won't actually prevent it from closing. It will just close without arguing or anything. So if a thread is a background thread, it does not prevent the application from closing. If it's a foreground thread, it does prevent it from closing until it's done. So because I made this a background thread, if I run this program, because once it does the main method, it comes in and it creates my new thread, it marks it as is background, and then starts the thread. Then it goes down and then it exits the main method. Once it exits the main method, the program ends. Because it's a background thread, the program's going to stop, and I'm not going to see any output. I may see the first one, I might not, I don't know. But once it exits the main method, the program closes, and the is background equals true causes it to completely stop. So let's go ahead and run it. As we can see, this time we got nothing. So the program instantly closed and nothing was displayed. If I run it again, we got nothing once again. So that's what happens. Now, because it is background. Now, I could do a couple things to fix this, but first I want to just uncomment the t.isBackground. Oops. If I comment this out, then it becomes a foreground thread again. And because it's a foreground thread, the program won't close until all threads are done. So if I run this, we'll see the output coming in now. So every second I get the next iteration of my for loop being displayed. And once this is done, then the program will close. And you can see it just closed now. When it says press any key to continue, it closed. So that's the differences between using it is background and is not background. So once again, if it's in the background and I run it, it crashes right away because it doesn't prevent it from closing. I could use, however, the command that I just taught you before, the t.join function, and that will make my thread wait until it's finished before it moves past this. So in essence, the program will never close until the thread is done. So even though I'm using a background, this is just a workaround to once again show you that this thread is actually running as a background thread. So if I run this, I will see the output. And then once it gets to 9, the thread will be done, and then it will finish, because t.join will then move on. So there we go, press any key to continue. That means the program has finished. Okay, so another thing with creating threads is, as you saw in the first listing, when we create a thread, and we created a new thread, and we put a method on that thread to execute when the thread starts. Let's say what if we wanted to pass a value to a thread when we started? Because last time we used the thread start delegate, and it said it required a function that had a return type as void and no parameters, so we couldn't pass it in. So what if we want to pass a value to a thread or a function to help the method along when it's running? Well, we can do that. So instead of using the thread start delegate, we're going to use the parameterized thread start delegate. So the first thing we need to do is, let's go ahead and create our function that our thread will be using. So we'll go public static void, we'll call it thread method, and this time we're going to take in a parameter. We're going to make it of type object because that's what the delegate requires. So we say object O. So being an object, we can actually pass in anything we want. We'll just have to use some unboxing, and we'll have to use some casting to use our type. So after we do that, our methods are going to simply take in a value. The value is going to be used in our for loop, and whatever the number they use, it's going to be the higher index of how high we should go in our for loop. So if they pass in a 5, we'll do from 0 to 5 or 0 to 4. So let's go for int I equals 0 as long as I is less than. Now if I just put an O, right, we're going to have some problems. O is what's passed in, but it's as an object. So I'm just going to cast that to an integer by going int O, and now we have our integer that was passed in, assuming that it really was an integer. So now we have that. We're going to do some console output by going console.writeLine thread process placeholder, and then we'll plug in our I, and then we'll just do thread.sleep 0. Now that, so this is our thread that's gonna, or this is our function that our thread is going to be using. Now let's go ahead and create our thread. So we'll go thread t equals new thread. This time we're going to be using a parameterized thread start, as you can see here, instead of just a thread start. So we're going to go new parameterized thread start, which is a delegate, and we can see that this delegate requires a function with a return type as void and a parameter of object, which is now that's what we have, right? So I can go thread method inside there. So we instantiated our thread. Now we're going to go ahead and start it. When we start our thread, this is where we pass in our parameter. As you can see, it has an overload for object parameter. So we'll pass in our parameter, and that will get passed in as the object to the function or to the thread. So we'll go t.start, and let's say 15. So we want 15 iterations on our for loop right there. And then we'll do t.join once again. So you all know what that means. So let's go ahead and run the program. And we can see that our thread, our brand new thread that we created, got the value that we passed into it. So this is one way that we can create threads and then throw it some information that it needs to perform its tasks on its own thread. So this is parameterized thread start. Okay, so now that we know how to create a thread, we know how to create a thread, a normal thread, we know how to create background and foreground threads, we know how to create threads that we can pass parameters to. Now we need to learn how we can stop a thread in its tracks before it finishes. So there are a lot of ways to do this, and I'm going to show you one way that uses local variables. Now, on a side note, because I'm using local variables, this can be rewritten, what I'm going to do, using global variables and using any other technique, but I'm going to be using lambda expressions, which are simply a shorthand for anonymous methods. Now, if you don't know what anonymous methods and lambda expressions are, I'm going to be making, if there is not already at this point you're watching this, I'm going to be making videos down the line that will explain anonymous methods and lambda expressions. So if you don't know what those are, I would recommend go watch something on that first if you are confused. If you want to just watch it anyway and you don't care about the lambda expressions, then that's fine. Now, anything with a lambda expression can be rewritten as a normal function. So I just want to put that on a note. So this example that I'm going to show you from the textbook uses lambda expressions and local variables, but you could rewrite it using normal functions and global variables, the same exact example. And you could use the same technique to stop running threads. So the first thing we're going to do inside the main function is we're going to create a variable called bool stopped, and we're going to set it to equal to false. And this is our variable that we're going to use that's going to control whether our thread should run or not. After that, we're going to create our thread, and when we create our thread, instead of passing in a function to it, we're actually going to just use lambda expressions to create the function inside of this main method. So we'll go ahead and go thread t equals new thread. We'll say new thread start. Normally, right here, we would specify our function, right? We want passing a function. But we can use a lambda expression to create a function if you don't know what lambda expressions are already. So let's go ahead and use the lambda expression. So we're going to have no parameters, lambda, or goes to. Now inside of our body of our function, we're going to do, this is our function code, so for when our thread is running. So when our thread runs, this is the code that's going to be using. This, like I said again, this can be rewritten using normal functions and global variables. So let's go ahead and say while we're not stopped. So we're saying while not true. So while false. So this will run as long as stopped, or as long as stopped is false. Yeah, pretty much. So while stopped is false, we're going to go console dot write line. We're going to say running dot dot dot. And then we're going to do a thread dot sleep for a second so it doesn't spam it forever. So that's our function. We have our function inside of our thread. So now we just have to just start the thread. So by doing t dot start, our thread is started and it's running on its own thread now. On the main thread, we're going to have output. We're going to say console.writeLine, press any key to exit. So if you press any key, it will stop this thread and it will cause the thread to close. So to detect if anyone has pressed a key, we have to go console.read key, and now we'll just wait at this line of code until someone's pressed the key. So therefore, if we get past this line of code, we can be certain that a key was pressed. So then we'll just stop the thread. To make it stopped, we just go stopped equals true. By marking stopped equals true, this while loop, which is using this local variable, which we have direct access to even on the main thread. So by accessing this variable, marking it true, once it comes around and iterates, it says while not true, well, that's false, so it won't run. And then that will break out. It will break out of the thread, and the thread will close. So that's what that's going to happen. And then we'll do a t.join to wait for the thread to end before we continue to close. So let's go ahead and run the program. So we can see it says press any key to exit, and it's going running every single second. Running, running, running. Now it will keep on running forever unless the key is pressed, because it's stuck into a it's in an infinite loop right now. Well, it's not really an infinite loop, but if I press a key, it makes stopped equals true, and this will break out. This is running completely on its own thread. So right now, the main thread is completely responsive. If we were building a GUI application or something like that, this is all running on a separate thread. So let's go ahead. If we press a key now, we'll see, boom, a key was pressed, and now it says press any key to continue, meaning the program has crashed. I can add a little output after this while statement saying console.writeLine, thread is about to close, right? Because if we're at this line of code, that means we're out of the while loop, and we hit this, the next line it goes to, the thread is going to close. So if we run the program again, we'll see the output. Now when I hit a key, it goes thread is about to close, and then it closed because we see press any key to continue, which means the program has closed. So like I said, this is one way to stop a running thread. We use local variables and lambda expressions, but this can be fully rewritten with other mechanics. Okay, so one thing to note about when we create threads is when we create a new thread, any local variables that are created inside that thread in that function are unique and private to that thread itself. Every thread has its own call stack, meaning that anything you create within that is only seen within, or is only a part of that thread, and it's completely private to that thread. However, there are ways that we can create different types of variables or fields or things that we can create, things that we can mark them as thread static. And by marking these things as thread static, every single thread will have its own copy of it. So threads can have data that is not local. The threads can have data that is unique to its threads that is not local. Right? So if we just create normal global variables, and create threads, any thread that accesses that global variable will all the threads will be using this shared resources, right? That they'll all be using that same global variable. Whereas if we mark these things as thread static, every thread that accesses that global variable will have its own version of it. So to do that, we're going to first create our global variable. So I'm going to say public static int underscore field. The reason why it's static is because we have static functions, and to access, we need to access only static data within static functions. So now we have that static function, we need to mark it as thread static. So we'll use the thread static attribute for the top of it. So this is the thread static attribute right there. Now that we have that, we're going to create two threads inside of our main function to help demonstrate that each thread is accessing its own thread static field. So to do that, we're going to create two threads. Each thread will be programmed to iterate over a for loop that will increment the value of underscore fields. So we'll increment the value of it, and we'll see that each thread is incrementing separate data because the maximum value is going to be 10, whereas if we're using the same data for each thread, that would grow even higher. So you'll see what I mean in a second. So the first thing we're going to do is we're going to create a thread. The first thread is going to be t1 equals new thread. We're going to say new thread start, and we're going to pass in a lambda expression once again. And once again, if you don't know what lambda expressions are, I recommend looking at other videos, or if you're watching this at a point that I posted my videos on those topics, then you can go ahead and watch mine. So lambda expression takes no parameters. Here's the body of my lambda, or my method. And then I'm going to create a for loop for int I equals 0. As long as I is less than 10, we'll say I plus plus. Every time we iterate, we're going to go field plus plus to increment the value by 1. And then we'll display to the console what the value is. So we'll go thread, this will be called thread A, and I'll display the value, so I'll go underscore field. Oops. So there's the first one. I'm going to create another thread that's going to do the pretty much same exact thing. It's going to be accessing the same data, but it's thread static, so we'll see a little difference. So I'm just going to copy and paste this. Oh, I forgot, we need to start the thread, t1.start. Now I'll go ahead and copy it. I'll do some renaming. I'll make t1, t2, t2.start, and what else? Make it thread B. So when I run this program, we see thread A first, so it goes 1 to 10, and then thread B 1 to 10. You can see that it didn't go 1 to 20. That's what if it was just normal data, it would go 1 to 20. But because they're thread static, each thread has their own version of this data. So when it increments from 1 to 10, it doesn't affect the thread B's 1 to 10 at all, as you can see. If I go ahead and comment out this thread static and rerun the program, we'll now see what I was talking about, 1 to 20. So you can see that it uses the same data, and when it runs the second thread, it just keeps on adding from the old thread. So our maximum value is 20 in this. If I put the code back in and rerun it, the maximum value will be 10 no matter what. Okay, so now that we have a little bit of the basics down with a thread class, let's talk about other ways that we can start using threads maybe in a more managed way. So for example, when we create a thread using the thread class, once that thread runs and finishes, that thread is destroyed and is removed from being able to be used. Now, there is a way that we can, however, use threads and then recycle them. We can add them to a thread pool is what it's called, and then whenever we need that thread again, or whenever we need to use a thread, we can pull that thread from our thread pool and use it, and then once we're done, we put it back to the thread pool. So this concept of using a thread pool allows us to save resources and reuse threads rather than always having to create and destroy them. Now, both ways have their benefits. You know, there's a benefit with using just the thread class because you have complete control with with when you're creating a thread or not. So you can create as many threads as you want, pretty much, and things like that. But there's also a downside. Whereas if you're trying to work with threads and you're let's say you have a server or something and there are incoming requests, if you let's say hypothetically you create a new thread for each incoming request using the thread class, you could create so many threads that it crashes the server and crashes everything and bad things like that. So whereas if you use the thread pool, it's more managed and the threads are recycled and it's more clean. So there's a couple ways to actually get into the thread pool. The first way I'm going to show you is using the actual thread pool class. So if I go, let's go ahead and create some thread pool actions. So we can go thread pool, and we can, in the thread pool has a function called queue user work item, and that queue user work item allows us to pass in a function, and that function, or use lambda expressions, and we can create a function, and this will queue the work, and once there's a thread available in the thread pool, it will run the work on this thread from the thread pool. We need to pass in an S4 state in this lambda expression. Then we're going to create our body of it. And once our thread runs, or our function runs, we're just going to display to the console working on a thread from the thread pool. And then because it's on the thread pool, we have no way to do, there's no join function because this isn't a thread. We'll have to just do a console.readLine, and this will just prevent, or this will allow us time to see the message. Oops. So if you go ahead and run this, we can see it says working on thread pool, and it's waiting for us to type in something, so it's not actually closing the program, so we can actually see the output. So we can see that our thread ran, and it ran our function using the thread pool. So this is using the direct thread pool class. Now there's another way that we can use the thread pool, and that's the next listing. Okay, so one of the problems with using the thread pool class is that we can't manage the threads quite well, meaning we can't tell when the thread has finished, or we can't tell if the thread returned a value. And because of those problems, Microsoft created this new concept of a task. A task is pretty much a managed thread pool thread, right? So we can create a task, and with a task we can monitor when the task has finished, and we can monitor if a return value came back from that task. The tasks use the thread pool as well, so all our threads are still being managed. Right? This is just managed thread pool threads. So to create a task, we can run a task by just doing task.run and passing in our lambda expression, just like threadpool.queue. We could do the same exact kind of thing, but task.run also has a return value, right? It can return a task. So once it runs the task, it returns the task, and then we can use that return value in that task to do things like getting the return value, or we can use it to wait until we finish that thread or finish that task before we move on. In the last example, using the thread pool, we had to use the console.readLine function to close the program, or to make the program not close so that the thread didn't stop. But with this, we can use something very similar to the t.join, or the join function of the pure thread class. The task has something very similar called the wait function. So let's go ahead and create a task. So we can first do task.run, but I want to set it equal to a task, so that we can manage it after we can get the return value of that task. So we'll go task t equals task.run. So task.run, it's looking for an action. An action is just a delegate that says we want it's a predefined delegate that says we want a function that has no parameters and no return type. There are overloads though, function, and you can learn more about these things when we talk about lambda expressions in other videos and things like that, and delegates. So let's go ahead and make a lambda expression. This is going to be our function. We could just create a function as well, and I'll do that after this. I'll create a function instead of using a lambda expression. I'll use a function just like this. But let's first just do this. So we'll have our lambda expression. We'll have our function now. Now let's go ahead. Inside our function, we're just going to do a simple for loop. And the for loop is just going to display 100 stars to the console. So we'll just do console dot write. Come on. Console dot write. And we'll do a simple star. I can't type today. Okay. So this will run our function on a new thread, hypothetically. We don't know, because it's using the thread pool and it's all managed. So we could do that, but because we're using a task, we can manage when the task is done. So we can go t dot, because t is our task. We set it equal to our task.run. Our task.run returns a task. So that's why this works. So we can go t dot, let's say, wait, which is the same thing as t dot join, right? T dot wait, or the wait function, just waits until this thread or this task is done with it before it moves on past this line of code. So let's go ahead and run this now. So we could see our 100 stars and it moved on. So this is our task. If I commented this out and ran it, you can see that we see no output, because before the task can even run, it closes the program, right? This is the difference. So by doing this, you can actually see that it is running on a separate thread. Because if it wasn't, if this was just a normal for loop, it would have to do the for loop first before the program closed. But because we're using a task, it's on its own. It's like creating a new thread. It's going to continue to close the program before it's actually done. So by doing the t.wait, we can make it wait until it's done before the program closes. Let's go ahead and do this again without using a lambda expression, just by creating a normal function. So let's go ahead and make our thread method function by going public static void thread method, and this is just going to do the code that is inside of the function now. So I'll go ahead and remove this. Now in our task, when we're making our task.run call, it says we require an action. An action is a delegate that's just saying that we need a function that has no return type and has no parameters. So because it's an action, I can just go thread method like that and just pass in my function. Okay, why is this erroring? Okay, so I didn't realize this was going to happen. So this is what you get for doing things without planning. So what the error is saying is because the task.run function can take in a couple of things. It can take in a function that is an action, or it could take in a function using the type delegate func. Now it's having a problem because it can't tell the difference between if this is just func or action, and because of how the method signature is set up. So if you don't, first of all, if you don't know what I'm saying with func and action, these are just predefined delegates. If you don't know what this is, you need to definitely have videos eventually of these, if not by the time you're watching this now. So you'll just have to go watch that and see what they mean, or look it up yourself. But pretty much, because it can't do it, I'm going to help it by using named arguments, and I'm just going to specify which one I want to use. So I'm going to go action and put a colon. This is the syntax for that. I think actually in this book it goes over what these are if you don't know what this is. So there will be videos in this series of videos. So I'm just specifying that I have an action. Is all I'm doing. And now this is the same type thing as before. I'm doing the same function call, the same task call. I'm doing an action. I'm just specifying my action instead. So if I run this, we do get the same output. If I were to comment this out, everything's the same. We can see that now it doesn't run. So I was just showing you that we don't have to actually use lambda expressions. If you don't know what a lambda expression is, there's always ways around it. And this might be a little confusing to you. But yeah, I don't have to use lambda expressions right here. I'm just using a normal standard function. Okay, so now that we created a task, now we can start getting a little bit more advanced with tasks. Let's go ahead and now try to get a task that maybe does an operation, but we're not going to do an operation, but maybe it does actually go do an operation, and then it returns a value from the task back to the calling thread or the caller. So that's what we're going to try to do with tasks. So it's going to be the same thing. We're going to set up a task and we're going to do task.run, and it's going to return a task. But this time, since we're going to be returning a value from the function, when we return a task, we're going to use a little bit of generics, and we're going to return a generic task. The generic task that's going to be returned is going to be whatever, it's going to be of type whatever that we're returning. So let's go ahead and set this up. So if we have, let's say before, this is how we did it before. We did task t equals task.run, right? This is what we did before. We made a lambda expression inside of our body of our method. We just did, well, this time we're just going to do return 42, right? So we're returning a value. Now that we're returning a value, if I highlight it over the run function, before it was just returning a task, now it's returning a task of int, because we know we have a return type where we're returning a value. So we need to store that value into a task. So instead of task t, we're going to make a task of int t. So now we're returning a type of int task. Now that we did that, we can access the value of it through the task down here. So we can go with console.writeLine t.result, and that will be whatever was returned from our function. It's going to be stored into this result property of the task. Now note, we don't have to use the wait method if we're accessing a result, right? So it automatically knows that to access the result, we have to wait until the function is actually done and the thread returns. So we don't have to explicitly write wait in this case. But if I run this, if I go ahead and run this, we can see that we do see that 42. So we did get the value returned from the task on a separate thread. Okay, another thing we can do with returning values from tasks are we can use continuations. And continuations are simply a way that we can do another operation the moment that task has finished its own operation. So we can use continuations. Now, there's a couple ways that we could do this syntactically, and I'm going to show you them. So like I said, just a note, a continuation is a way that we can do an operation the moment our task finishes. So once our task finishes, it will do the continuation portion of the task, and that will just be whatever I told it to do. So to do this, I'm going to make a continuation of my task that will just multiply the 42 by 2. So to do this, I'm going to go, there's a couple ways to do this. I'm going to use this extension of this function call, and I'm going to go dot right here. I'm going to do continue with, this is my continuation right here. Continue with. Now, it requires a, as you can see, it requires a, I can't speak right now. The continue with function takes in an action delegate. The action delegate requires an action of task int. So that means I have to supply it an argument that will hold in a task int that's going to be passed in, right? So with an action, this is just a quick little thing on actions if you've never heard what they are. The action delegate, an action delegate is always a return type as void. So in its generic properties, anything that is in there are considered all parameters. So since in my action delegate right here, you can see it says task of int, that means I need a function that has a task int as a parameter. So using lambda expressions, I don't have to specify. If I was using a function, I'd have to specify it more. Using lambda expressions, I can just simply go, I in this case is going to represent my task of int, and that task of int is simply just the task of int that's coming from here. like because we're using the continue with extension form of this, we're coming from this task event, so we're gonna get this task for this this task. I don't know what I'm saying right now. Sorry. Okay, so there's our I right there, which is gonna be a task of int. So now we need to set up our lambda expression. And inside the body of our expression, we're going to multiply it by 2. So in here, we'll say return I.result, because it's a task of int, that will hold, this has the 42, times 2. By doing that, now we returned it. So now this is our complete task right here. So it gets this 42, it does whatever it needs to in here. We did a continuation, and then it continues with multiplying by 2, and then it does a return, and then here we are. So at this point, this console.write line is, if this program if we were to start this program right now, it would wait here until this task is done with the continuation and everything, and then it will display the results. So if I were to run this right now, we do see that the 84 is displayed. So once again, the reason why this works is because when we do the continue with right here, the continue with does its stuff, and then the continue with actually also returns a task of int. So if we wanted to do it separately and do another multiplied by 2 continuation, we would have to go something like this. Let me first frame it out. So we would have to do t dot continue with down here, right? We'll create our lambda expression once again. That's going to do the same exact thing. And then once again, we'll do return I.result times 2. So this is to do the same exact thing. But if I run this, nothing's going to happen, right? It's still going to say 84. It didn't multiply it by 2 again. And that's because the continue with is a continuation, and that returns the task of t as well. So I have to make this work, I have to go like something like t equals. So I reassign it to our existing task. That's what this does. This syntax right here, if I just attach it to the function call of the first task, it will automatically return it and place it into this task right here. So if I'm doing it separately, I have to just reassign it to my task by going t equals the continue with, because the continuation returns the task of int. So by doing this, now I get the value that I'm looking for. So that's a continuation. Okay, before I move on to the next listing real fast, I'm going to combine the next listing I'm going to combine the next listing from 1-10, so I want to combine 1-11 also with this because it's very similar. It uses continuations. So I'm going to delete this real fast. So pretty much there's other things that we can use continuations for, right? We can the continuation or the continue with function has an overload that takes in other things. So we can add continuations for a bunch of things. For example, I'll do 2 of them. We can add a continuation that if an exception is thrown within that task, we can make a continuation that will automatically, if it's faulted, it will enter the faulted continuation, and then it could do some code that we need to do depending on whatever happened. So to do that, we're going to do a continuation. We're going to go t.continue with. Same thing, so we're going to go I. This is going to be our task of int right here. Then we make our lambda expression. Inside there, we're just going to say, okay, this is going to be the one if we get an exception. So we'll say faulted inside of this. Now we're missing one last thing in this. We need to specify the continuation. So we need to go inside of the continue with. There's an overload that we can specify what we want. So we're going to specify not a cancellation token. We're going to specify a continuation option. So we're going to go task continuation options dot, and we're going to do this if it only on fault. So if it faults, then we'll do this continuation. So if we run the program, so there is no fault right now, nothing happens, 42, everything's good and dandy. But if I were to create an error by going throw new exception and then running it now, I got an exception throw. The program crashes because it's not managed. or handled, but I do see the faulted continuation go off. So that's another way we can use continuations. I'll do one more of these. I'll do another continuation. We could do one for if it was successful or completed. So to do that, we require the continuation option of an only on ran to completion. So every single time we run it now, oops, I didn't delete the exception. Now every time we run it, we'll always hit the continuation or the completed continuation. So that happens if it was completed. If we hit a false here, it wouldn't actually run the completed one because it wasn't actually completed. So the continue with function does have an overload for more things like this. Okay, for time management purposes, if you're following these videos from listing to listing like I do from the textbook, I am skipping listings 1-12 and 1-13 for time management purposes. I do try to cover as many listings as I can, but these listings aren't as important in my eyes. They're very simple. So I'll quickly explain. In listing 1-12, it's pretty much just explaining that we can create parent and child hierarchies of tasks. We can create tasks, and we can put tasks inside of other tasks. By marking a task as a parent, or by marking a task as a child, or by attaching it to the parent, we can use continuations and things like that by making okay, let me reiterate this. We can use parent and child tasks to make the parent task finish only when the child tasks finish. So you can create a hierarchy like that. I mean, in the listing 1-12, they do that, and then they create another task using a continuation of the previous parent task. So in that hierarchy, the child tasks have to finish first, then that causes the parent task to finish, and once that parent task is finished, then the continuation would kick in, running the final task of displaying all the results or something like that. Listing 1-13 is the same exact thing, just instead of using and having to attach each child to the parents in that syntax, it uses the task factory to do that dirty work of making child tasks. So besides that, it's very basic. You take a look at that. If you guys want to see this example for some specific odd reason, you can just go ahead and leave a comment, and I will go back and do these. But I want to try to get this video done so it's not too long. Okay, so I want to pick up on listing 1-14. Okay, so another way we can use tasks are by using multiple tasks and having multiple tasks running at the same time. And we can manage those in many different ways. So one thing I want to show you about if we are using multiple tasks is the first thing. I think I have a couple other ones to show you as well. The first one to show you is the WaitAll function. And it's similar to the task.wait function that just waits for that task to finish before it moves on. The task.waitAll waits for, if I'm using multiple tasks, waits for them all to finish before it moves on. So to show you what that looks like, let's go ahead. I'm going to create a task array. And this task array is going to hold 3 tasks. I'm going to say my first task, or task 0, equals task.run lambda expression. Here's my method body. My first task is going to be equal to it's going to be just thread. I'm just going to make it thread.sleep for a second, and I'm going to display to the console the word or the number 1, and I'll return 1 as well. I'll do that. I'm going to copy and paste this 2 more times for the 2 other ones. So I'll make this the second and the third, and 2, and then 3. So by having this, I create 3 tasks, and I'm going to run these tasks almost simultaneously. Now, if I do this right now without using any wait function, I run it, nothing happens because the program ends. These are all tasks. It moves right through them, and the program terminates. But if I want to wait for them all, I could, let's say, for instance, wait for one of them. And they all are sleeping for 1 second, so they would most likely all display. But if I, let's say, if I made this one 2 seconds and this one display after 3 seconds, if I try to go, let's say, tasks sub 0 dot wait and ran this, and then ran this code, it runs the first one, it waits for the first one, and then the program closes because that's all we're waiting for. If I want to wait for every single task, we can use this task dot wait all function, and we can just pass in our tasks array like that. And by doing this, it will make sure all tasks are finished before the program closes. So this is how we can manage that all. Now, if we make them all 1 second again, in reality, if we didn't use tasks, this would take 3 seconds to run, right? It would have to do the first one, the second one, and the third one would take 3 seconds. But because we're using tasks, every single one is being ran at the same, sort of at the same exact time. So using the task.waitAll function, we can wait for all the tasks to finish before we move on with our code. Okay, another function that the task class includes is the task.WaitAny function. Now, this is particularly one of my more favorite functions in the task library or the task class, and this is a cool function because of how it operates. So pretty much the task.WaitAny function's job is to wait for a task, or if we were waiting on an array of tasks, just like the wait for all or wait all, just like that, the WaitAny waits for an array of tasks or any kind of task collection, and if any of the tasks finish, then it continues. So it's only waiting for any of them. It's not any particular one. It's waiting for any of them. And you may be thinking, "Oh, I don't really see any purposes for that." But there are some purposes, and it's pretty cool, the purposes. Now, if you just use it as the task.WaitAny, like how we used it before, there's no real purpose for it in that way. But if we use some creative things with it, we could make a cool program. So here's a little simple sample. So we're first going to create an array of tasks again, but this time it's going to be an array of task of ints, because each task could return a value. So we'll make it a task of int, and we'll make an array, and we'll call it tasks. Tasks again. Let's zoom in. Task array tasks equals new task, and we're going to have 3 of them once again. So let's go ahead and assign these some values. So the first task is going to be equal to a task.run, a lambda expression, and we're just going to do a thread.sleep 2000. We're going to make all the threads.sleeps different so we can see them when they finish at different times. And this is going to be a return 1. That will be the value of this task. Let's go ahead and copy this and just do this again for 2 more times. 1 and 2. Make this 1 second, 3 seconds, 2 and 3. So our first task will sleep for 2 seconds, return a 1. The second one will sleep for 1 second, return a 2, and the third one will sleep for 3 seconds and return a 3. So now we have our tasks set up. Let's go ahead and make a while loop, right? We're going to have a while loop, and this while loop is going to continue for as long as our task.length is greater than 0. So as long as we have a task in our task array, this while loop will go on forever. So you can assume that what we're going to do is, as tasks finish, we're going to display the result and then remove it from the array. As we remove from the array will get smaller and smaller. Eventually, it will stop the while loop and then continue on and close the program. So what's going to happen is it's going to display the data to the console as it finishes. Now, you can only imagine how powerful this really is. If we were using some real, if our functions and our tasks were doing real operations, going off and doing real things, using something like this is so powerful because we can display things and do things, like we could display things to the users as they finish their tasks while keeping while keeping the graphical interface always responsive. This is very cool. So what we're going to do is inside our while loop, we're going to use the WaitAny function, and the WaitAny function returns the index of the function or it returns the index of the task in the array. So we're going to store that into an I variable. So we're going to say tasks.WaitAny, passing in our array of tasks. So it's going to wait when the compiler comes in when the program comes in and runs this line of code. It's going to wait at this line of code until a task completes. Once it completes, that index of that task will be stored into I. Now that we have that index, we can get the complete task because we have the index. So we can go. I'm going to store that task into a task variable. So I'm going to say completed. I can't spell. Completed task equals task sub I. So we'll pull out that task. Then we're going to write the value of the task that was stored. So we're going to say completed task.result. And that result is what we get from either return 1, 2, or 3. So we'll display that result. And the last thing to do is we need to remove this task from the array. So we're gonna create a temp variable that we're going to convert our array into a list. By making a list, we can then remove it from the list. So we'll go temp.remove at, and we'll remove at index I, and then we'll reassign it to the task by converting it back into an array. So we convert it to a list, removed, and then convert it back to an array. So this is a really cool program. I really like this program. If we run it, we'll see as they finish, they're displayed. So you only can imagine if this was a real operation and they was doing real operations, how powerful this really is. I really like this. So we're creating 3 separate tasks. They run at separate speeds, and as they finish, the main thread will handle and display the values only because of the task.WaitAny. I mean, we could use the task.wait for all or wait all function, and once it's finished by using task.wait all, we can then just go iterate over the task and display all the values. I mean, we could do something like that. I mean, there's so many ways to do this, but the cool thing about WaitAny is that we're actually being able to display it the moment that task is finished without having to wait for all the other tasks to finish. Okay, so now that you have a basic understanding of what tasks are and how we use them, I want to talk about another class that lives in the same namespace in system.threading.task, and that class is the parallel class. The parallel class has a couple of static methods in it that are interesting. It has a static method called the for method and a for each. Both of these parallel for and parallel for each are very similar to their counterparts of the regular for and for each constructs. However, these functions don't run sequentially like the regular for and for each do. These run in parallel. So when I say they run in parallel, I mean that iterations of the loop can run at the same time as another iteration, right? They don't run sequentially. Like, it's not necessarily ever going to go from top to bottom iterating over the loop. It can go in any order because they're running. Some of them may be running at the same exact time. The iterations can be concurrently going on with other iterations. So that's the cool thing. And I'll show you what I mean by that. So parallel loops can run in parallel. They can run, some of the iterations will run at the same exact time. Now, because of this, it can do a couple of things. I mean, one, if you're using them right, and the data that you're iterating over doesn't need to go in a certain order, then it could increase the speed of the loop dramatically, and I'll show you what I mean by that. So let's start off by just doing a basic for loop. I'm going to go over the parallel for, but I want to show you in contrast with the regular for loop. So let's do int I equals 0 as long as I is less than 10, I plus plus, and every time it iterates, I just want to write to the console the I, the number, and then I want to sleep for 1 second so we can see how long it takes to do each iteration if we're actually doing some kind of operation inside of it. So if I run this, we can see how slow this goes, right? 0, 1, 2, separated by every second, so this is going to take like 10 seconds to complete, which is pretty slow. So this is the regular for loop. Now, if we convert this and use a parallel for loop, by doing this, each iteration is concurrent or can be concurrent with other iterations, and that could make it go a lot faster. So down here, I'm going to write this in a parallel version. So to do this, we have to use the parallel class. We'll go parallel dot, and we can see our functions that we have. So we're going to use the parallel for. So inside of our body, it's sort of similar like the for loop, but a little bit different. We have the start index, so we'll go 0 in our case. Then it's the to index, so it's going to be 10 in our case. The third part is going to be the body of it. So this is it says we require an action of int delegate, so that means a function that takes in an int parameter, and that int parameter, the int parameter is going to be the value it's incrementing or going up. So we'll say I is going to be our int. Then we'll set up our lambda expression. I mean, we don't have to do a lambda expression for this body. We can plug in another function because it's a delegate, right? We can give it another function, or we could use anonymous methods. But besides that, so this is our body. This is how we set up the parallel for. It's very similar. So this is the 0 is here, the 10 is coming from here, and the I plus plus is automatically doing that in the background, but this I is pretty much this I represented right here. And this is our body, which is the same as here. So I'm just going to copy this code and put it right into there. So I'm going to comment this old one out. I'm going to run it now. This is the same exact program, the same exact code, but I'm using a parallel for loop now. So if I run this, oh wow, I can't even move it over by the time it's done. Okay, I'll try to do this fast. Actually, I'll just put a sleep here, so once it starts, so I'll go thread dot sleep for 2 seconds. Then I'll do a console, say start. So once it says start, that's when the loop actually starts. I'm only putting the sleep in so I can move the window into view before it starts. Alright. So you can see, the moment it said start, that is when the parallel for loop went off. And the first one with the same exact code with the regular for loop took 10 seconds. And this took about, 2 seconds to do this one. And it's doing the entire loop. It's going in and doing everything. We have that sleep in there to create an imaginary delay as if we were doing a long operation. So even with a long operation, it was doing all those long operations at the same time because it's all concurrent with a parallel for loop. So we're doing them at the same time. So I'm just trying to emphasize that we're doing the same code. You might be thinking, well, how is it going so fast if we have these sleeps in? And the reason is because maybe it's being thrown on all the iterations, and could possibly be thrown on different threads, or however it's doing it in the background. They're running in parallel, so it always is still doing this sleep. So we're creating that delay, but because we're doing it in parallel, it still is so fast, right? The only downfall to the parallel for loop is that we can't predict the order, right? With the for loop, we know it's going to go from 0 to 10 every single time, but with the parallel for loop, we don't know. Like when I run it, you can see the order of the numbers are out of order because we don't know how it's going to do it because it's doing it in parallel. It's all up to that. Like it gets completely out of order. We can't predict the order with this. Okay, so that is the parallel for. Now the same thing is for the for each, right? For each is another type of loop. And we have the same exact thing with the for each. So I'm going to first demonstrate it with the for each again. and then I'll demonstrate it with the parallel for each. So to start off, I'm just going to create an array because for each is good for iterating over a collection, right? So I'm going to make an int array, call it my array, and I'm just going to set it equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So that's my array, and I'm going to do a standard for each. So I'm going to say for each int x in my array. I'm just going to display that to the console, and then I'm going to go ahead and do my thread.sleep, and then just run the program. And as you can see, there's the same thing as that standard for loop, right? We're going to get that same output. It looks like this. So now let's go ahead and convert this to a parallel for each loop, which will dramatically increase the speed, like I said. So let's go ahead and do it down here. Parallel for each. So in the parallel for each, all it does require is we just pass in the collection or anything that implements IEnumerable. So that will be an array does. So we'll pass in the array, and then we need the action, or we need a function that has a parameter of integer. So we'll go ahead and create that. We'll go create the body, and this is the same thing. So I'll copy the code in. Okay. Now I'm gonna have that same problem again, so I'm gonna put a sleep. Oh wait, I called it I. I'm gonna put a sleep in, and the same thing. So I'll do thread.sleep 2 seconds, just so I have time to move the window over into view. And then when I do console.writeLine start, once it says start, that is when the parallel will kick in. So let's run the program. I move it over. Okay, to start. Boom. Boom. So the regular for each took 10 seconds again, and this one took about 2 seconds, or I don't know how fast that ever was, because you can see each time, like every second, it was popping out like 5 of them, right? So we can see that it was maybe put on 5 different threads, or however it was set up. That's what it's doing. So this is what a parallel, the difference between a regular sequential loop and a parallel loop, right? The parallel loops can run things in parallel. It can run each iteration in parallel, meaning at the same time. Okay, so before I continue on to the next little listing, which is 1-18, I want to quickly just go over again why we use multithreading in asynchronous processing. So just so you remember, we use multithreading for 2 reasons. The first reason that we use multithreading is we want to exploit the capabilities of using or programming in parallel, meaning doing things at the same exact time. So using multithreaded programming, we could take advantage of the amount of cores we have on our processors by running things at the same exact time. So that's one reason why we use multithreading. Another reason why we were using multithreading was to always keep the UI, or to keep the program responsive when we were doing long tasks. So with multithreading, we want to keep everything responsive. Now that second reason, with keeping things responsive, there is another way to do that, and that is using asynchronous programming features and concepts. Writing asynchronous code involves using threading, but it doesn't mean that asynchronous coding is multi-threaded programming. Asynchronous is a pattern that we use, that we can use threading to make asynchronous work. And in the release of C# 5.0, there was 2 new keywords released, the async and the await keywords, that allow us to or help us write or help us use asynchronous code more easily. The first thing to note about these 2 words, async and await, are that these words directly don't are directly not involved with creating threads. So when you see the async and await or async and await keywords, they aren't being used to create threads. These keywords are more used to for the continuation of tasks, or the continuation of threads. They're used to control threads and tasks. So with the release of these new keywords, the .NET framework or the .NET libraries have all been sort of redesigned to implement new asynchronous functions that we can use. and those asynchronous functions always make sure that the UI thread or the calling thread, it stays responsive, and we can use these async and await keywords to make sure, or to help control the continuation of these asynchronous features, because when we call these asynchronous functions, they are running asynchronously, so we need to control that by using these two keywords, so that we can get the return values from these functions and we can tell when they're done, things like that. So asynchronous functions are normally used when we want to help keep the UI responsive when we're dealing with things with I/O or input and output. And there's a lot of applications that this can be applied for, whether it's reading stuff from disk or reading stuff from over the network or downloading things and things like that. We normally use asynchronous techniques to keep everything responsive. So let's go ahead and do an example using these keywords. So the example is pretty basic. We're just going to create a function that's going to go ahead and go download some content or download the HTML code of a website. The function that we'll be using will be in the HTTP client class, and it's called a getStringAsync function. So that the asynchronous function, in this case, we're going to be using one that was already defined for us. So we're going to instead just be using the async and await keywords to help us with managing that and the continuation of when the asynchronous function gets back to us. That's what we'll be using these keywords for. So let's go ahead and create the function that's going to be going out and getting the data. So let's create the function. I'm going to say it's public static, and then we need to mark it async. When we mark our function async, I can't type. When we mark our function async, that's not actually doing anything asynchronously. That just tells the compiler that there is going to be asynchronous code inside this function, or that we're going to be using the await keyword inside this function. This function is going to return a task of string, and the reason is because asynchronous functions go off and they return tasks back to the caller. So we're going to return that task that we get all the way back to the main thread, or the caller, the calling function. Okay, and then I'm going to go ahead and call my function download content, no parameters. Inside the body of my function, I'm going to use the using statement. I'm just going to create or instantiate an HTTP client wrapped in a using statement. Now I'm going to call the asynchronous function using the await keyword, and when I use the await keyword, that will return the result, or it will return the result of the task, because the asynchronous function returns a task of string, and I'll store that task into a string using the await keyword. So if I go string result equals await client.getString asynchronously from HTTP from Microsoft.com. So I'm going to go ahead and do client.getString, so it's going to get the string of that. This is going to be returned, as you can see, a task of string. By using the await, I await that, and when I say await, the program flow waits here until the value of the function gets returned. So we're waiting until it gets back. Now, while we're waiting, because it's asynchronous, we are keeping the thread open, and it's always going to be responsive. Also, when we say the await keyword, this allows us to convert it into the string for the result, and then we'll store that into result, and then we'll go ahead and just return the result back to the caller. Okay, now that we have that, let's go ahead and build the main function, and this is just, we're going to store the result into a variable from the download content, and the download content is going to be coming to us as a task of string, so we're going to access its result property for the value, and then we're just going to display the result to the console. So if we run this, we can see that we downloaded the code, and then we display it to the console. Now this is all done asynchronously because we called it asynchronously using the built-in function from the framework. We use the await keyword to make sure that we keep or we wait until we get the value from the function besides moving on. So if we didn't use the await keyword and we moved on after we called this async function, the program flow would have kept on going on, and then the variable, the data that we are getting back from the async function wouldn't have been stored anywhere. So by saying await, we're waiting at that point until we get the code back, or until we get the value returned back from the async function, and then we can store that into the string variable. Okay, because the length of this video is extremely long, and I did not expect it. The first objective in this book is huge. So the videos that are going to be after this are definitely not going to be as long as this, but this first objective was really, really long. So because of the length, I'm going to stop the video here. The only two topics that I didn't cover that would be after this were p-link and concurrent collections. Now these two topics are really basic, so it's okay. But I'll quickly explain them without showing any code. Really quickly, p-link, which stands for Parallel Language Integrated Query, is simply link in parallel form. So we worked with parallel, for, and for each loops, and that's the same thing with link, right? So in link, we can query over collections, or we can query data, and that's a sequential query normally, which is regular link. But if we use p-link, we can do those queries in parallel, which just means that the queries can be running at the same time in parallel. Like how we did the for each and for parallel loops, we can see that multiple ones of them were running in parallel. So that's the same thing with p-link. It's just parallel language integrated query, or p-link. The last topic in this objective was using concurrent collections, and concurrent collections are really basic also. We know that our collections that we use right now are like lists and dictionaries and queues and stacks and things like that. So a concurrent collection are those collections pretty much, but they are thread safe collections. One problem when we use multi-threading is that we need to make sure that we don't specifically to collections, we need to make sure that no two threads are accessing a collection at the same point in time, because that's bad, because for example, if one thread is removing data while the other thread is trying to access that specific element that just got removed at the same exact time, there can be problems. So whenever you're dealing with multi-threaded programming, you always have to deal with synchronizing access to collections. So the concurrent collection classes are used that are thread safe by default. You don't have to worry about the synchronization in those collection types. So that's what concurrent collections are. I'm pretty sure, let me double check. The next objective is managing multi-threading, and that's going to be talking about synchronizing resources. So we'll be talking about how we can make sure everything is thread safe when we use multi-threaded programming. And that video will definitely be a lot shorter than this. I did not expect this being so long. There was just so many topics in this. So that's it for this objective. Thanks for watching.